Welcome to Microwave Engineering lecture series. In this lecture, we'll discuss about the conditions of input impedance and transfer impedance. So in last lecture, we discussed up to this deriving this input impedance. So now we see this input impedance, conditions of input impedance. So here you can see this. The input impedance is maximum of pi minus 2 beta is equal to 0. So what we do is for L, so we get of pi by 2 beta. So pi minus 2 beta elements which is equal to 0. So this term will go here and this pi will bring downside. So we'll get L length will become as pi minus 2 beta L. So Z maximum is equal to R naught into 1 plus K divided by 1 minus K. So this input impedance is maximum level is R naught into S. So we know this S will be the standing wave ratio. So next is along if the transmission line, along the line if the wave is traveling. So at the distance of lambda 4, that is a quarter wavelength transforming from one point to other point. So we get the impedance will be the maximum at one point and the minimum will be the other point. So this we assume this length, already we seen this length L is equal to pi by 2 beta. With that we'll add the quarter wave transformer, that is lambda by 4. So we now what we do is we cross multiply this term. So we get, after solving this, we get of pi plus pi divided by of phase by constant propagation was divided by 2 beta. So now what we do is L is, we know this length of the transmission line like pi plus pi divided by 2 beta. Now again we do the cross multiply. So that is the for maximum. Now we see this what will be the Z minimum point. Last we have seen the what is the Z max, that is R naught into S. So now we see this what will be the impedance of minimum, that is ZS is equal to R naught into 1 plus K. This already we have seen this term, how we derive this term. So now we do what we do is instead of 2 beta L we substitute this pi plus pi. So after solving this term we get of R naught into 1 plus K divided by 1 minus K. So the Z impedance at the minimum point will be the R naught by the Z. So now this we see the condition of dissipation less line when it is short circuited and it is a open circuit. For short circuited, the ZR will become a 0. So after substituting this in this formula, we get of ZS is equal to J into R naught of tan beta L. Okay, and so this that is a standing wave ratio, that is of S. So now what we next is the for open circuits ZOC, for so that ZR will become as infinity. After doing this cross multiply, we take this ZR as an outside. So we get a 1 plus R naught J tan beta L divided by ZR. And this term after multiplying R naught by J beta L into ZSC by R naught. So here we again we do the cross multiplication, this multiply, so we get XS by ZR. So ZOC is equal to J of R naught C plus beta L, which is equal to J of XC. So for varying this length with this respect to of input impedance, we calculate XS by R naught is equal to tan beta L. So by variation of length 0 and 0 to this lambda, that is by quartering this lambda by 4, lambda by 2, 3 lambda by all this thing we have calculated when it will become 0 and when it will become as infinity. Based on this equations we have substituted here. And similarly when it is of open circuited, this XS by R naught will become as cot beta L. So here we assume this when it will become as an inductive line and when this line will become this capacitive line, that we'll see in the next slide. So this is the input impedance for the open circuit and short circuit lumped components. So this we can say as we have designed with the respect to lumped components like with inductance and capacitance. So here we can see this if the line is closed, that is we call this in inductive, and here by varying the length of the line we can see it is in either it is in inductance or it is in the capacitance. For this lambda by 2, that is length of the line, this will be inductance and capacitance will be in the series form with the small resistance of that is input impedance for the different wavelength of short circuited line. And similarly for the input impedance for different wavelength the open circuited line, so this will become as a open, so this will be as a capacitive, and this is also an inductive. So for this we assume this it will be in the parallel form of tag circuit of LC component with the high resistance. So next is the transfer impedance. So this transfer impedance we denoted as a Z is equal to Z sending end voltage divided by the receiving end voltage, that is Vs by IR. So this Vs equation and IR equation already we have derived from the general equation series solution that we can see in previous lecture series. So now what I do is I take this Vs term. So we know this Vs is equal to Vr by 2 into 1 plus Z naught by Zr e power of gamma L plus 1 minus Z naught by Zr into e power of minus gamma. And now what we do the cross multiplication and we take this term as an outside. So we get e power of gamma L, and this when we take this term as an outside, this will come in this denominator. So we get this term as e power gamma L plus Zr minus Z naught divided by Zr plus Z naught. So now we know this Vr is equal to IR into Zr. So this Vs is equal to IR Zr by 2 and Zr plus Z naught by Zr into e power of this term. So this Zr will get cancelled. Again we get off this term IR will become as we bring to the denominator here. Vs by IR is equal to 1 by PL will have only the 1 by 2 into Zr plus Z naught e power of gamma L plus Zr minus Z naught of e power of minus gamma. Now we know this Vs by IR is equal to 1 plus 2. Now again we do the multiplication here, Zr into e power of gamma L minus plus Z naught into e power gamma L. This we do this term as an e power gamma L plus e power of minus gamma L. So again what we do is we take this term, we say this as a cos h of gamma L with so this cos h gamma L plus Z naught into of sin h of gamma L. So Z is equal to Z naught Zr plus cos h gamma L plus Z naught into sin h of gamma L. Thanks for watching. In next we'll discuss about the reflection coefficient and reflection loss.